Okay, so our next presenter is Rahul sir. He will talk about how to Monte Carlo and machine learning.
Thank you. So yes, hello everyone. I'm Rahul. I'm a PhD student at the Indian Statistical Institute in Kolkata. And this work is based on two of my publications, one in JCAP and one in the Astrophysical Journal. So it turns out we are still not sure how fast our universe is expanding today. So that is the well-known Hubble tension, the infamous Hubble tension, which as it turns out, as of a few days ago, it's standing at 7.1 sigma, which is a very serious issue. So this is a discrepancy between the measurement of the Hubble constant between early time measurements and late time measurements. But here we wanted to take a different approach. We wanted to see, well, why not? Why look at early and late? Why not look at intermediate redshifts? Now this is can be made possible with gravitational waves. The reason being that gravitational waves travel further distances unimpeded, and you can get the distance from the waveforms directly. Of course, subject to the condition that you can also localize the redshift. So once you have that, you'll be able to determine Hubble constant independently as an independent probe from gravitational waves from future missions. We can't yet detect events at that higher redshift. Since we can't detect events at that higher redshift yet, what we can do is we can do simulations. We can generate mock data sets. So this study is sort of a forecast study. It's not it doesn't deal with real data. So we generated multiple mock data sets for different source populations, for different fiducial cosmologies, and also for two different missions, the LISA and the Einstein telescope. And for each of these sets, we took two different sets of current data to feed as the fiducial information, each based on an early time data sets and late time data sets. Using all these different catalogs, we forecasted using three different methods. First, the Fisher forecasting method, which gives you an estimate on the errors. Second, we did an MCMC analysis as if the mock data is completely real data. And the third was a machine learning reconstruction technique, which gives you the Hubble parameter h of z and the Hubble constant h0 as a result of the intercept, independent of any cosmological model. So we did this, and this is a slew of results here, but the main conclusions that we found out from these results is that Gaussian processes, this machine learning technique that I'm referring to, is a very robust method to reconstruct the Hubble parameter and hence get the Hubble constant when these future missions give us data in terms of GWs. We also, our forecasts also yield the fact that the Einstein telescope and LISA will constrain the Hubble parameter, the Hubble constant, to much higher precision than all current data sets combined. And of course, this sounds obvious, but our results also show that the longer the missions run, the more detections we'll have, and the better the precision we'll have on the Hubble constant. So we are not solving tensions here, but we are saying that gravitational waves will have the capability to give us precision enough to definitively tell us what the Hubble constant is. Whether it's in the early regime or the late time regime, we don't know, or whether it will lead to a tripartite tension, we don't know. But that is what makes this very, very interesting. So yes, the only take-home message that I wanted to say is whenever you do forecasts, please do it using many different methods so as to comparatively weigh and outweigh the pros and cons of each and to get a fuller picture. And yes, I'll stop here. So I welcome you to my poster. If you want to know more, you can write to me later if you have any questions, or if you want to know more about what else I do, you can visit my website. Thank you.